To quote Joe Biden, it's a big effing deal. Okay. Now, you should really Google that. It's pretty funny. I love that. It's pretty humorous. Now, anywho, what I want you to do, we're going to do a little visualization for just one moment. Just close your eyes. All right. Just close your eyes, dude. Cole, close your eyes. Everybody's closing their eyes but you, loser. And how would you know if you weren't? Shh. Now, picture yourself. You're 18-year-old boy, 6'3", blonde guy. And, wait for it, there is this stunningly beautiful, that 6-foot-tall blonde gal walking down the street toward you. Wow. Wow. Now, first and foremost, in your mind as a 6'3" young man, does this really stand out to you? Yes or no? No. Yes, it does, Matt. And why is this, Matt? You were going so good, and then left turned into the wall. All right.
3. I mean, thank you. I'm under.
Shh. Now listen. Focus. Now, yes, this stands out to you. This stands out big. This stands out pretty big. Yeah, you're like 5'8", 5'9". That's pretty tall. 5'10", that's pretty good. 6 foot. Wow, that doesn't happen every day. It doesn't. Now, again, you're supposed to be focusing here. Now, this is just one gal. You keep walking down the street. Why do I see eyes? You should not see the eyes open. Close your eyes. You keep wandering down the street. What town are we in? Doesn't really matter. Just keep walking down the street. Here comes a gal 6'2". Walks out of the store. And you're like, okay. You keep walking down the street further. Hey, look, there's another gal. She's 6'2". There's another one that's 6 feet. 6'1", 5'11", 6'9", 6'4". Who's 5? At this point, what are you starting to feel like? Everywhere you go, all the women are over 6 feet tall, or right around 6 feet tall. What are you starting to think about your first thought?
You're out of basketball terms.
Shh, no. Your first thought was this 6-foot gal was out of place, yes? But that was based on what? Based on your assumptions and or prior history. Yes? Okay, you can look now. Thank you. We'll close them again in a minute. Now, this is a big deal. We know from general experience that most gals are 5'5", 5'5", 5'6", 5'7"-ish. We know that because that's where we live. Can you stop talking? Thanks. Now, anywho, we know that coming in because we know everything we know we've been conditioned to that. We've collected data over the years, so to speak, in our brains. And we're like, that's pretty normal. That's pretty normal. Now, again, if it was just one tall woman, do you think much about it other than go, oh yeah, she's pretty tall? No. You don't even really blink an eye. You just go, oh, that's weird. Or if you're the certain young man I was thinking about, you're like, yeah, all right. But you make note of it, but then perhaps you move on. Okay? Maybe it takes you a while to move on, but you move on. Okay? But here's the deal. If, however, you took a sample, just some random sample, what if the average of that sample was 6 feet tall? Is that weird? That's pretty weird. But what, Jake? Were you going to say, where you said, did you go, mm-hmm, or did you say, well? I thought you said, well. That's pretty weird. So listen, so if you took an average of a sample of girls, and the average they were quiet till you showed up, was 6 feet tall, would that be weird? Well, first thing that comes out of my mind is, how big a sample, Mr. Groom? 2 girls? 3 girls? No. Let's go big. Let's say there was 40 women in the sample, and the average of that sample of 40 women was 6 feet tall. Does that weird? That's really weird. Now, what would you expect to happen in a sample of 40 women? Would you expect to have like a 6-footer in there? Would you also expect a 4'10"er?
Yeah.
And would you expect a whole bunch of 5'6"s and 5'7"s and 5'4"s and so forth? Would you expect a bunch of this stuff? And wouldn't you expect it, wait for it, to look something like, oh, I don't know, like that? Yeah. Turns out, yes, because we know that heights are normally distributed, yes? But today we learn maybe the coolest formula. It's 2 parts to it. First part is this. As we take a bigger sample, is the variation of the averages going to change much? No. Because we're going to see hardly any variation at all. Look, I take a sample of 100 women over here, 100 women over there, 100 women over here, 100 women over here. Geez, you know what? They're almost exactly the same. Now, how about that? Now, inside the sample, you're going to see some highs and some lows and some of this and some of that. But the averages, if you compare this average from this sample to the average from this sample to the average from this sample, hardly any variation at all. Yes? So this is a 2-part deal. Now, so the first part is this. So first of all, the central limit theorem deals with averages from samples. Deals with averages from samples. I left an A out, but you know what I mean. Okay? So the first part of this is this. Okay? As the sample size gets larger, there is less variation in the sample average. Okay? So when we say sample size, we mean the letter n. So as n gets larger, there's less variation in those sample averages. You can compare an average from here, there, and everywhere. You can take a sample of 100 people here, and 100 people there, and 100 people there. Oh my gosh, we got almost the same exact average. Well, duh. How about that? If there's only 2 people in my sample, could I see quite a bit of variation? Yeah. Because you could see a 6-footer and a 5'10" gal, and you're like, wow, I got a really high average in this sample. Over there I got like a 5'2" and a 5'3"er. That's a very low average. That's quite a bit of variation. But if I take a big sample size, like 30 or 50 or 100, I'm not expecting to see hardly any variation at all. Hardly any at all. That's a big deal. As a matter of fact, this is true. The sample, the variance, the standard deviation will be this. Okay? So our x bars will have a standard deviation that's equal to the standard deviation what it was originally, in this case for standard deviation for all women's heights, divided by the square root of the sample size. So now we happen to know, this is a fact, you can take it to the bank, that the standard deviation for the height of women is about 2 inches in America. About. It's pretty close. Okay? So if I did 100 samples, the sample size of 100 women, I would expect to see a standard deviation. It would be equal to, for the sample, to be equal to 2 divided by the square root of 100, which is 0.2. I would expect only 0.2 inches for a standard deviation. Meaning that just like we thought, there's very little variation. It's not going to change much at all. It's a big deal. That is probably the most important part of this. Now, going forward, keep in mind that we drew this picture, right? We've drawn a bunch of these pictures where we said that we know that the women's heights were normally distributed. We've drawn this picture like 72 times. Where we put 66 inches here in the middle, yes? And we said that 68 and 70 and 72, 64 and 62 and 60, right? I've drawn this picture a bunch, yes? Where this is one standard deviation, yes? Right? But Mr. Haynes, that is for a single individual. You see that? For a single individual. But if you took a sample of 100, this picture wouldn't look like this anymore. No, siree, Bob. It would look like this now. 66 would still be in the middle. Huh? But guess what? It's going to be 66.2, 66.4, 66.6. And subtracting going the other way, 60, what? I can't subtract. 65.8, 65.6, 65.2, yes? And so this, what I'm going to see is it's still going to be a normal looking curve like that, yes? But not as spread out now. In other words, it is not that weird. It's not very likely, but it's not very weird to see a woman who is 6 feet tall. It's not really very normal, but it's not very weird either, right? But if you were to take an average of a sample of 100 women, dude, 6 feet tall is over here, like 22 standard deviations away or something ridiculous. Is that weird? Yeah, it left weird in the dust miles back. Okay, like 70 miles back. It is freakish. Okay? So that's a big part of why we study this, okay? Because as we take sample sizes, we get rid of a lot of variation. It doesn't take much change at all to say, whoa, wait, stop, hold the phone, something's wrong here. Okay? Now, we're going to spend a great deal of time second semester with this sort of thing. If you're going to be running a plant, for instance, a manufacturing outfit, would you like things to go really far awry and make a whole bunch of crappy product and ship it out before you realize there was a problem? Or would you like to catch it like right now? Well, I want to catch it right now. Well, the cool thing is if you take a sample, it doesn't have to change very much to go, wait, stop, hold the phone, there's a problem. Maybe even only like, a few tenths or thousandths of an inch. And you're like, wait, stop, something's screwy here. Don't waste the product, don't ship it out, don't lose people. I went on Yelp, I'll never buy their product again, and off it goes, okay? So we'll deal a lot with this second semester. Oh boy, will we ever, okay? But that's part one. Part two is this. And this is probably the most important part of it. This is the huge part, friends. It says regardless. Regardless. What does that mean? It means it doesn't matter. Regardless of how the original data, and we'll call them the x's, yes, is distributed. You mean it doesn't matter if they're normal or not? That's literally what regardless means. Yeah, it doesn't matter. All right? This is important. The x bars, that is the sample averages, are distributed normally with the same mean as the x's, but with standard deviation equal to, as we mentioned on the previous page, this guy. Now, this is what we're going to say. It says the x bars are distributed normal. They have the same mean as they originally had, but their standard deviation is now cut down by the square root of the sample size. Now, we already mentioned this, and this is part of it. So this is obviously part of it. As n gets bigger, the variation gets smaller. We already said that. But here's the critical part. It doesn't matter how the original data is distributed. I mean, it could be binomial or hypergeometric. Yes. Or Poisson. Good job. Glad you remembered it. Yeah, anything. Doesn't matter. The x bars are always normal. And if they're normal, then by God, I can make z-scores for them, and I can find percentages from them. You with me on this? That is a big, big deal. You cannot underestimate that. What's the matter, dear? What can't you read? What squiggle? Oh, is distributed. I literally, it is this bit right here. It's just, I'm just saying all of this crap, which is that. It's a big deal. Now, prove it to me, Mr. Groom. I'd love to. Let's do it. Now, perhaps, let's have a number cube. I mean, like a dice? Literally like a dice. Now, if a person were to roll this dice, let's say 120 times, what would the histogram look like, basically, of what we got? What would it look like? If I rolled it 120 times, in theory, what should it look like? What? I heard it. What? Straight? It's pretty much like this? Yes. Literally, it should look like that, right? Because they are what we call a uniform distribution, yes? Should be 20 of each, right? Is that normal? Well, no, because normal looks like this, right? That ain't normal. So this is the easiest one to work with. So I'm going to use this one. Now what I'm going to do is I'm going to generate some random numbers. Wait, we did that. Well, some of us did. Some of us were still waiting to see our simulation project turned in. But whatever, who's counting, right? Not my grade, it's yours. Anywho, let's bust out the Excel, shall we? By the way, if you, there's maybe one or two of you, but I emailed it to you and you still haven't graded it because you're a jerk. Again, we've already established that this is true. Then, okay, you could remind me again because, sometimes a guy forgets. If it's on his desk, it's hard to forget stuff, but when it's in a folder online, you just kind of forget about it because it's not sticking out, glaring at you every day, mocking you on your desk. Now, I'm going to, again, generate some data. How many data points are you going to I feel like I'm going to do random numbers, and I want to roll the dice 100. I want to roll 100 dice, and I want to roll each of them 1,200 times. Okay? You with me on this? It's going to be 100 columns, each 1,200 units long. It's pretty good. It's going to be good. We'll see what happens here. Now, input data is here. We know how to do that. We've done it before. And voila. And while it's thinking, I'm going to get my rodent. It's going to take a minute. All right? Yep. Wow. That was faster than I planned. It is a lot. You're not wrong. Now, dang. It's like 1,200 times 100. All right. Now, I'm going to scroll, clear the bottom here real quick. Oh, there it goes. I overshot it. Figures. All right. Now, watch what Mr. Groom's going to do here. Equals average of, and then it's going to do the old A1 to A1200. What? Like so. Well, what should it be, Mr. Groom? I feel like we just did this last chapter. What is the expected value, or the average, of this guy? Well, it would be 1 times 1/6 plus 2 times 1/6 and all the way across. Turns out it's 3.5 exactly. Okay? We did that last chapter, so that should not be shocking to us at all. Now, oh my gosh, Mr. Groom, it's 3.4 on this column. It is. But we have, 100 of them to go. So I'm going to grab them all. So click on this dude. Take off a dragon. Whee! And is that it? That's it. Boom. So there they all are. Geez, I'm shocked. They're all right around 3.5. I'm not shocked. I'm not shocked. I'm also going to copy them. I'm going to do two things with this. I'm going to copy it. And then I'm going to go into a new sheet somewhere. Maybe I am. I don't know. And I'm going to hit, I'm going to do this and it's going to get mad at me. God dang it. Oh, you're so stupid. You knew that was going to happen and you did it anyways. Wait a minute. I got to do this first. I got to hit paste I got to paste values first. Copy it again. Oh, hippie. All right. Well, we'll get there in a jiffy. All right. There it is. I'll try it again. Copy. Copy. There you go. I'm going to transpose it this time. Do it right. Voila. Nice. Now, Mr. Groom. Hey, this is important. This is 100 averages, yes? How many possible different averages could there be? Hold on a thought. Every time I roll the dice, how many chances does that dice have of landing up right one way or the other? 6. and I do it 1,200 times, isn't that 6 to the 1,200th power? Right? Wow. How many of them, of the total of them, do I have? Hardly any. Okay. So keep that in mind. If you took all of the sample averages, which you can't do, they would have the exact same average as the actual distribution, which we know is 3.5. So what are you going to do here? Well, I'm going to average what I do have. What I do have is 100 of them. So I'm just going to go and see what's up. No, 100, right? 100, dummy. Yeah. Shh. There it is. 3.4975. Can you get a whole lot closer than that? I feel like it's going to be hard to get much closer than that. Now, wait. We also did this, so you may recall, where we would go in and we'd sort like this, and we'd go, oh. Shh. So let's do this. Let's make a histogram. So A100 minus A1 is 0.275. Now, it's been a while, but you're like, hey, that's the range. You're right. Let's make a histogram, let's say 7 bars, shall we? So if I take that fella, divide by 7, 0.036, yes? So we should always round up, call it 0.04. Are you with me on this? Hmm? Now we can do this a couple of ways. I'm just going to do it this way because I feel like it, I guess. 3.355 I'm going to go with for my lowest bound. It's not really that important, but I'm just going to count by 0.04. Was there a problem?
Yeah, I have a question.
Yeah, hit me.
Okay, so you know the 0.036786?
Yes, dear.
Why did you divide like the number before that by 7? Like the point.
Do what now? Divide by 7?
Yeah, why did you?
Because I wanted 7 bars on my histogram. Put your phone away. Thanks. Because I wanted 7 bars on my histogram. Because I felt like it.
Okay.
Remember, 5 or 7 is kind of the key, but you could do anything. I'm trying to make a quick histogram here. What I want you to see is it's normal looking. That's what I want, okay? So I'm trying to sell you on the bit about how, oh my gosh, Mr. Groom is totally right. He's not lying to us about this being normal looking, hopefully. So hopefully you buy that. I don't really care if you do or not, I guess, because it's true whether you like it or not, right? But hopefully you agree with me once you see it and you'll be like, whoa, how cool is that? What? What? Look at that. It's like, it's almost as if it was like normally distributed. That's weird, dog. So, format data series. Let's lose the old thigh gapperoonie. Boom. What? It looks fairly normal-ish. Okay? It certainly is not flat anymore, is it? Mm-mm. By the way, notice that before we went all the way out to 6 on the one end and all the way out to 1 on the other end. Bro, the smallest we got is like 3.3 something. The biggest we got is like 3.6 something. That's the biggest we got. That's hardly any variation. I know. That's what it says to us, yes? Now, back to the notes page. If you'll recall from the other day, we knew how to do this too, didn't we? It was the sum, so it's going to be 1 times, it's 1 squared times 1/6, and so on and so on and so on, yes? I'm going to cheat a little bit because I happen to know that I can do this, and that plus mean. And so we've done this before. It's not the end of the world. And they're all multiplied by 1/6. Another way of saying it is all divided by 6 when you're finished. And then minus 3.5 squared. That's the standard. That's the variance. And so it's 36. It's 61. It's 77, I think. It's 86. It's 90. 91. 6th, I think we'll see. Minus, this is 12 1/4. I happen to know that one. So if you'd give that to me, that'd be swell. Actually, you should probably add those up just to double check me. 36 and 25 and 16, 9 and 4 and 1. Okay? Remember that this is the variance of the actual. What? It's like 3 point something when you're done or something. 2.9. That's literally basically what I said, but okay, cool. Basically. And of course the square root of that is what? It's 1.7-ish, isn't it? 1.7.
1.7.
Good enough for government work. Okay. Now, wait for it. Wait for it. Because this one happened to have an average of 3.5. Yes? The actual sample did. The actual sample had a variance, or a standard deviation rather, of 1.7. But I'm telling you that the X bars from our sample size of 100, this is a big deal, by the way, that it's of a sample of 100, because if it was 40, it would be the similar deal, but it wouldn't be as tight because the standard deviation wouldn't have got so small. It'd be a little fatter. If we'd taken 1,000, it'd be quite a bit scrawnier at that. So what we're going to see is that this is distributed with the same mean, but it's normal now. I'm sorry, did I forget the normal? It's normal distributed. We've already showed that. With the same mean as the original. But the standard deviation should be, in theory, 1.7, that is the original, divided by the square root of 100, which of course is 10, yes? And if you'll allow me to do the math on that's 0.17, isn't it? Nice. 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 Now, that's great, Mr. Groom. Go back to the chart over here and show me that on the thing. I'd love to, if I can find it. Where's my data? Can't find my freaking data. Is this my page with the data on it? Yep, no. But no, that's the wrong page.
I believe it's in the first sheet.
Nope, there it is. I found it. It's right here. It's right here. This is the one I want to use. So equals ST deviation, oops. You hippie. That one. And A1 colon A100 is 0.05. And you're like, why is it so different, Mr. Groom? Well, 0.05. Yes, well, here's the thing. You are going to have instances, you will have instances where it's a little off on this one. This one's a little weirder. But in theory, it should be the 0.17 bit. Okay? It's not the end of the world. Just be aware of that. Okay? Now, if you go back, now, the key and the long and the short of it is this. Anytime I say to you, anytime, I give you a problem like this, it doesn't matter what it's about. Suppose I take a sample of 40 people. And I find that their average eyelash length 2.1 centimeters. I know that's long. It just makes for a better problem. And the standard deviation from this sample. By the way, that would be SX from the sample, yes? All right, because I took it from the sample. And this, of course, is X bar because I took it from the sample. Okay? All right. If I were to take a sample of this sort of thing, okay, when I do this situation here, what is the problem? You know, we can do any number of things with it. So when I look at this situation, there's that. So let's back the train up just a skosh. I get carried away sometimes. I get so excited. If I knew that this was true, if the standard deviation was 0.2 centimeters initially, if I knew that's true, then what's the probability that my sample of 40 has an average greater than 2.15? Okay? Now your first thought is, well, geez, 2.15, that's hardly any different at all. I know. But let's look at it this way. First of all, do I know anything about the eyelash lengths of humans? Are they distributed normally? My guess would be that they are, but I don't care. I don't care. Because I know that the averages are distributed with the same mean, so 2.1, and a standard deviation of 0.2 divided by the square root of my sample size. Now, if you don't mind, what is 0.2 divided by the square root of 40? Get a second. 0.2 divided by the square root of 40. Point something, I don't know. 0.03 or something. 0.03-ish. Okay? So if a person were to, and this is normal, I keep forgetting my normal. That's kind of a big deal. If I were to come over here and draw myself a normal curve like so, are you with me on this? I'm going to put 2.1 in the middle, of course. If I count off by 0.03, 2.13 is here, right? 2.16 is here. Well, where's 2.15? It's in here somewhere, isn't it? Now, without doing the math, that's a little over 1 deviation above the mean, correct? And you're interested in finding this amount out here, true? So how do we do it, Mr. Groom? Well, we should make a z-score. And here's where the only part that's a little different. It's going to be x bar minus the mean over sigma over the square root of n. Now this is a big deal. This is for a sample. This is for a single person, is what we did last week, or 7 months ago, or whenever I last saw you. Okay? For a single individual, it's this fella. You're like, Mr. Groom, couldn't I just put a 1 into here for n? That's true, but listen, this is a big deal. This only works if because this is just one individual, the actual x would have to be normally distributed down here. Okay? And then a person goes, well, wait a minute, if I only took a sample of size 2 and it wasn't normal, wouldn't that be a little weird? It is. We have a way of fixing that later on. Hold tight. Stay with us, okay? We'll tune back into that. So right now we've got a sample size of 1, which means it had to be normal to play this game. That's what we did last week or 2 weeks ago or several weeks ago. And now we're doing this fella. This one up here means it does not matter, not even one little bit, what the actual x is. It doesn't matter at all. We're just going to use this formula, and away we go. I would suggest for some of you, you know who you are. Maybe you don't. I don't know. A lot of you should actually take this step and actually write it out like so. Then I would draw this picture, because it literally takes 2 seconds to draw that picture. And then you're like, oh my gosh, this should be like 1 point something in a minute when I'm done. I know, you know. And then it's pretty straightforward from there on out to know that you're at least in the right ballpark. Okay? But a lot of you lazy people will be like, I don't need to do that. You do, but you don't anyway. That's fine. It's your deal. I don't care. So 2.15 minus 2.1 over 0.03, which, by the way, is this thing here. I already did it. You see that? I already did it. Okay? Now, I've been doing it long enough that I don't normally do this extra step right here. I don't actually compute necessarily. Stop it. I don't always compute that guy. Sometimes I just go with this bit up here. You with me on this? But I think it's helpful to actually compute it and then draw the picture. Now, what does that come out to be? 1.6 what? 7. And how do we find the probability that is greater than that? Well, on my TI calculators, I go, are you with me? I go to the normal CDF, yes? And I put in my lower bound, 1.67, and my upper bound, which would be E99. And we're home free, yes? How do we do it on our spreadsheets, people? We go this. We say, because it's an upper one, we go equals 1 minus norm dot sdist, right? And on the Google Sheets, it's no dots. I think it's just norm sdist, but whatevs. 1.67, comma 1. And this always gives you the probability that it's less than or equal to, so then 1 minus that puts it on the upper end. Yes? And what do we get for an answer? 0.04. 0.04. Yay! So there's a 4% chance, all right, that you will find an average of 40, what did I say, 40 people? Of 40 people where their average eye length is greater than 2.15 rather, centimeters long. That's about an inch. That's kind of weird. For inch eyelashes. Even fakies, that's pretty long. Yeah?
I answered my question.
Oh, excellent. Let's do another one. Now, like, after a while, won't this be really fast and easy? Yeah. But let's do another one, shall we? So, yes. Yeah, I don't know. So, maybe you know that the average amount of algae in a pond is, I don't know, 30, no, 30 square feet. I was going to do percentage, but I'm not going to do it. It's 30 square feet. 30 square feet. I don't know. I just made that up. I don't know. I don't know. What is standard deviation? Depends how big a pond it is, I guess. Standard deviation of 5 square feet. I don't know. Not really that big a deal. Yeah. By the way, we totally could have used percentages, and we will next chapter. It's going to be the bomb. You will see. Stay tuned. Okay? Now, so, obviously you can't do all this at one day. But a person can say, well, we could test that too. We can. We're not today. But yeah, we could. So let's say you take a sample of 50 ponds. Mr. Grimm, why did you use algae in ponds? Because that's the first thing that came to my mind. But second of all, I don't think it's normally distributed. But it doesn't matter. Okay? What is the probability that X bar, that is the average of that sample, is less than 28 square feet? Okay. Now you look at that and you're like, wow, 28 square feet, that's pretty close to 30. That's right. Oh, but hold the phone a minute. We know that X bar for this sample of size 50, yes, is distributed normally with the same mean, so 30. But our standard deviation will be 5 divided by the square root of 50. Square root of 50 is 7-ish. So this is 5/7 is a 0.7-ish when you're all done there. What is it? 0.7. Good enough for government work. So again, I would suggest that a person draw this picture out like so. 30 is here. We're only talking about going less than, so I'm only going to go this one. It's going to be 29.3. Are you with me on that? Subtract 7.7 more. It's going to put me at 28.6. Go 0.7 more. It's going to put me at 27.9. Are you with me? I'm not just making that crap up. You can see where I'm getting at. Now, where are we at? We're talking about 28. Hey, 28's right here. You with me? So it's like -2 something when I get a z-score, yes? Well, let's make it. So x bar minus, again, mu, divided by sigma over the square root of n, that's what we're doing here, is equal to, of course, it's going to be 28 minus 30 over 0.7. And as we said, it's going to be -2.8. Beautiful. So how do we find that? The probability that x bar is less than or equal to 28. I say it's normal CDF, yes? And I put in negative infinity to -2.8. On the calculator, on the computer, of course, it's just normal S-dist, -2.8, comma 1. Right? In sheet, you don't have to use the 1. Even freaking better. Which, by the way, doesn't make sense to even have to do that, because what does a normal PDF do for you? Nothing. Because normal PDF, what's the probability that it's equal to any one number? On a normal distribution, what's the probability that it's equal to any one exact number? 0. The probability that it equals any one number exactly is 0. Right? And again, that's because there are infinite possibilities, yes? So that you would select one of them, 0. For those of us that have had calculus, you're like, it'd be integrating from A to A, which just makes no sense. What's the area of a line? It doesn't have any area. Okay? 0.00?
0.002.
Or thereabouts. Okay? Yay! Apparently you need to fatten up. Okay, now, let's do, hey, shh, can you stop making a racket? Thanks. Now, let's do one that is normally distributed, okay? Okay, like, wait for it, women's heights. So, you happen to know that women's heights are normally distributed. Mr. Groom, you're really riffing on this one. I know, just go with me. It's fine. Now, now let's sample one woman at random, okay? Just blindfolded, pull out a name, go find her. Wow, you're 5'2", or you're 5'12", or you're whatever you are. I don't even know.
5'12".
What is the probability that this one woman that we select is somewhere between 5'5", which of course is 65 inches, and, no, I don't know, 5'10", sure, which is 70 inches. Okay? That's all we're saying. Now, this is one woman. Yes? So, this picture, because it's already normal, looks like this. 66 is here, of course, 68. Mr. Grimm, you really riff on it. I know, just go with it. 70, 72, 64, 62, whatever. Here's 65 is here. Yes? Here's 70 right here. Can we find that percentage? Well, I feel like we can. One of them is going to be like -0.5, yes? And one of them is going to be +2 for z-scores, yes? And of course, to make those z-scores, one would simply go 65 minus 66 divided by 2, which is -0.5. And one would also do 70 minus 66 divided by 2, which is +2. Geez, I'm shocked. I feel like I said 70, but I think I said 70, but it's all right. Anyway, what else? All right, now, on our calculators, of course, we do normal CDF, -0.5 to 2. On sheets, we do it in two pieces, yes? Yes, on sheets, we do it for the 2, and we do it for the -0.5, and then we subtract them, yes? And if we get negative, we should have subtracted it the other way. Nice. Anyway, what do we get? 0.97. Holy buckets. Are you telling me that we have a 97% chance of reaching in and selecting a woman at random, and that woman's height would be somewhere between 5'5" and 5'10"? That's literally what we're saying to you. That is correct. That's correct. Okay? Now, notice that this is for one person at random, yes? Now, let's take a sample, shall we? Let's take a sample instead. So let's take a sample of n equals 36, shall we? Okay? Now, we know that it'll have the same exact mean. But now, the standard deviation will look like this, which, as you know, is 0.6666. Yes? Hate you. I don't know how to draw. So now my picture looks like this. Here's 66. Here's 66.666. Here is 67.333. And here is 6. Try again, Jay. Try 68. There you go. Yes? Yes? Because I'm adding 2/3, yes? And if I subtract 2/3, it can put me at 65.333. Right? Subtract 2/3 again, it's going to put me at 64.66, and then it put me at 64 over here, yes? Yes? I feel like that's true. So look, 65 is now here, yes? Look where 65 is now. A minute ago, 65 was -0.5 deviation, yes? Now it's -1 point something deviations, true? All right? But where's 70 this time? Ah, it's over here, dude. It's over here like, wait for it, how many deviations would that be? Well, I don't know. You got to go 4 divided by 2/3, right? Which then if you divide that out, it would be like 12, 6. It's like over there, 6 standard deviations. Now we know, where's the entrance to Freakville? Roughly 2 deviations is the welcome to Freakville sign. 3 deviations is you are now entering downtown Freakville. If you are 6 deviations above the mean, that is just wow. Wow. Now, listen carefully. I guarantee you, if you do this on your calculator, if you do on your spreadsheets primarily, bless you, dear. If you do norm s dist, and you put in 6 standard deviations, because that's what it's going to be. Because if I do 70 minus 66 divided by 2/3, I get 6 standard deviations. This calculator will likely tell you it's 100% or less than that. It will say to you, it's really 0.99999. Screw it, we're going to call it 1. Okay. Now, on the other one, of course, 65 minus 66 divided by 2/3 should be 1.5, negative 1.5. Okay? And so on my calculator, of course, normal CDF, negative 1.5, comma 6. And it should basically be what? What's that? 0.93. Okay? Now, up here it was what? 0.97. Down here, 0.93. Yeah, so what happened here? Something goofy. Let's go back up and look at this top one again. That one feels weird. Can we double check that one? It feels odd to me. I feel like it's not that. 60 something sounds better.
It's 60.66.
60.60? Yeah, whatever. That's better-ish.
Oh, shoot. I put it on.
Thank you for screwing up my lesson, but that's okay. No, I'm just teasing. Now, listen, friends, shh. This is a big deal. Whenever you're asked, by the way, on a test, I guarantee there'll be questions like this one. Guaranteed. Where they ask about an individual, and then they ask about a sample. The sample will always have a higher probability of happening if it's an in-between deal. Always, 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 always. It's got to. Okay? Now, on the outside, that's a different story. But on the insides, always, 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 always. Here's a question. Suppose that you know the in St. Helens real estate prices, the average price, 180 grand. I don't know, I just pulled that number right out the usual orifice. Okay? Standard deviation, I don't know, 20 grand. Yeah, just made that up too. I don't know. Nobody cares. It's just a problem. Suppose you take a sample of 50 homes. What is the probability that that average will be greater than $197,000? I don't know. Yeah, I don't know. I don't know. Now, this is probably normally distributed, but it may not be, but nobody cares. We're taking a sample, yes? So we know that these guys are distributed normal with the same exact mean. But the standard deviation is 20 grand divided by the square root of 50. What does that come out to be? 20 divided by the square root of 50 is 2,000 and something, I think. Yeah, that sounds about right. Sure. So if I were to draw this picture, right in the middle I'd put the 180, yes? And then 182, 828. Now I can't do the math in my head here. I can't do it. But what's the next one? If I add 28, 28 again, I'm going to get what? 185, 600 and something. And then, wait for it, 187, 188, 400 or something, okay? It's not really that important. Okay? Where is 197 on this chart? It is way out here. Yes? What percent of the homes will be a greater than that? None of them. Yes? Basically none of them. Yes? So again, how will I do it? Well, I would do 197 minus 180 divided by 2828. And I'm going to see that there's some god-awful huge amount of standard deviations above the mean. It's ridiculous. What does it come out to be? I can't do this in my head. But it's clearly way out here. You don't need a rocket surgeon to see that. Just don't. Or even as like a crystal ball person. You don't need nothing like that. Yeah. Six standard deviations? Nice. So again, normal CDF. We're going from 6 to infinity. Sheets people, you're going to go 1 minus. Normal S just 6. Yes? But in essence, it's going to be 0, yes? E minus 40. What? Oh, E minus 10. 9E minus 10. I'd buy that for a nickel. Yeah, so basically 0, yes? Yeah, it ain't going to happen. Ain't going to happen. That's it. That's all. Yeah, nothing much to it. Yeah, not at all. Now, what I'd like you to do the rest of the next half hour is get busy working on page. Oh, I didn't bring my book. Save it. You all have phones. Take a picture of someone next to you's book and get busy. Now, page, I'll tell you what page in a second if I find it. Be handy.
338 through 20.
Probably.
Because that's our next.
It is 338. Beautiful. 10 to 20. Beautiful.
Because for some reason my pencil went missing.
How do you lose